Now let's continue our discussion and move on to the next topic. So what we have discussed just now is how to calculate the unit impulse response. That means you have a special input. That special input is your delta function. And also, keeping this in mind when we talk about unit impulse response, we're still focusing on the zero state response kind of thing. Okay. So we're assuming for the system, the initial condition is assumed to be all zeros. So the next question is, well, this is only a very special type of input. How do we extend the discussion right here, assuming we know how to calculate h of t? How do we extend our knowledge to find the zero state response to any generic signal based on h of t? Well, this is the problem we're going to answer now. Now, before finding the input, finding the output to any input signal, let's look at our delta function. Okay, let's look at our delta function, which looks like this. Okay. And if we put this delta function through an LTI system, then the zero state response, based on our knowledge and something we discussed before, is going to be h of t. Okay. This is the unit impulse signal. This is the unit impulse response. Now, let's modify this signal a little bit so it will be easier for us to understand. Instead of looking at the spike, let's look at a rectangular signal. Starts at time 0 and ends at time equal to delta tau, where delta tau could be a very small number. And I constructed such that the amplitude of this delta is going to be 1 divided by delta tau. The reason I am constructing this is the following. Let me call this delta hat of t. So it looks like our delta function, but it's a little different. Now for delta function, we know if we take the integral delta t dt from negative infinity to plus infinity, we're going to have it equal to 1. Now if we do this integration for our delta hat from negative infinity to plus infinity, we also have it equal to 1 because we simply have to, the integral should be equal to the area of this narrow rectangle, which will be the width delta tau multiplied by the height, which is 1 over delta tau, and it's equal to 1. So in this sense, the two are sort of enclosed to each other. And as we can imagine, if the width of the signal goes towards 0, that means it becomes narrower and narrower. At the same time, if I keep the height to be 1 over delta t, the height or the amplitude becomes larger and larger. Along this direction, our delta hat of t will also be approaching the delta function we have over here. Now, if this logic makes sense, and if we're putting this signal into the same LTI system, and let's assume the corresponding output we call h tau, sorry, h hat of t. And using the same logic, when tau goes to 0, if the input delta hat looks like delta t. The output h hat most probably will also approach h of t, the actual unit impulse response. Okay. So if this guy move along and approach this, the output probably will also move in the same direction. If we believe this to be true, then we can do something. Suppose we have a generic input signal. And we call this input signal f of t. Let's say this input signal look like this. Okay. And what we're going to do, let's say the origin is right here. What we're going to do is that we'll make a copy of it. The origin is right here. And what we're going to do is we're going to split the time axis into small intervals. And each interval will be of width of delta tau. So we'll have 2 delta tau, 3 delta tau, 4 delta tau, and so on and so forth. And what we're going to do is we're going to construct a signal such that at time 0 I find this corresponding point. Instead of having a curve, I'm going to make it go flat until it reaches my delta tau, and I will drop to look at the intersection and make it flat again. Then we'll see another intersection right here. Let it go flat, find another one, go flat, find the other one, go flat, find the other one, go flat. And every time I will just go flat for delta tau. So if we do this, okay, we can do this on the other side of the signal. So we're kind of constructing a copy of my ft, and if you only focus on the screw staircase going up and down, if I call f hat of t, so it looks like f, but it's a different one. Now, these two pair of signals are not too far away from each other. Again, if I let delta tau goes to 0, we probably can imagine f hat of t will be approaching the original f of t. So when the stairs becomes narrower and narrower, of course you're actually approaching the curve that we started with. The same logic applies to what we had before, and same logic. Now, let's look at all of these staircase in a different manner. Let's look at it as a bunch of rectangles. Okay, let's look at it in a bunch of rectangles. Now, this rectangle is what? This particular rectangle looks just like the rectangle we have up here, right? It starts at time 0 with width equal to delta tau. The only difference is the height is probably not equal to 1 over delta. So let's see how we can modify this. Now for this particular guy, if we want to write delta hat of t, there's one thing we need to mention. We need to know the amplitude. The amplitude right here should be equal to what? Should be equal to f, the original curve, evaluated at time 0. Right? And it should not be the original amplitude, which is 1 over delta tau. So if we go back again, for this particular guy right here, if we divide the height, if we take delta t over 1 divided by 1, 1 divided by delta tau, this will generate this rectangle, still with delta tau, but the height now will be equal to 1, since I divided into the actual height. And now I further multiplied by the height of the curve at time 0. This will only means I'll end up with this rectangle. This is one of them. I can find all the others. For instance, if I want to find the second rectangle, what do I do? It's actually the same delta hat, but shifted to the right, so t minus delta tau, by this amount of distance. And I don't want to have the amplitude of 1 over delta tau. I wanted to have the height equal to the curve evaluated at delta tau. So this will be the second rectangle. I can move on to the third one if I want. And the third one will be what? The third one will be another delta hat, another this thin rectangle, but moved to the right by 2 times this delta tau, because it starts at 2 delta tau. And again, the height is not going to be 1 over delta tau, but at the curve evaluated at 2 delta tau. And I can do this for all the rectangles, the thin rectangles before and after. And if you want to add everything together, apparently this is going to be equal to f hat of t. Because this entire staircase is just simply the summation of all these thin rectangles. And if I figure out one of the rectangles, I can figure out all of them. If I want to express f hat of t, I can simply add all these rectangles together. That's what we're doing here. But it's looked a little messy, writing down all the terms. So what we're going to do is we're going to find a common term, or a common form. Apparently I need a summation since there are a bunch of terms. And each of the terms that we're going to do this, have this in the summation, we should have this delta, this narrow, this thin rectangle, and we're going to have t, and we're going to shift this rectangle to the right and to the left by a multiple of delta tau. And this n, maybe let me use k since we use n already. Let me use k. K is just an integer, could be positive integer, could be negative integer. Okay. But in general, we may have infinite number of these thin rectangles okay, on both sides of the origin, so we're going to have this infinite summation. So take care of these rectangles. Then multiply by f, the curve evaluated at k delta tau. So evaluate right here is 0 delta tau, 1 delta tau, 2 delta tau, and we're going to have 3, 4, and so on. And if you see if it's minus 1 delta tau, you have f of delta tau. Minus 2 delta tau, you have 2 delta tau. And lastly, don't forget this term need to be taken care of. Since it's divided by 1 over delta tau, we'll just simply multiply this delta tau. And this is a new way to express this f hat. And as we know, if delta tau is small enough, and it goes to 0, we're going to have f hat t goes to f of t, the original or the actual input. And if we believe this to be true, and assume that for the linear time invariant system, that the output of f hat of t is y hat of t, and the original input f of t will generate the output of y of t. Then delta t tau goes to 0. This rectangle becomes thinner and thinner, will basically lead to y hat of t approaching y of t. In other words, if we can find a way to evaluate y hat of t, or to approximate it, or to evaluate, to calculate, then by taking the limit of delta tau go to 0, we may be able to find a way to calculate y of t. And remember, we didn't specify anything about the input, so this result may be extendable to any generic input. And let's see how this can actually be calculated. And we're going to use two properties of the system. One is called linearity, the L, and the other is called the time invariance, the Ti. We're going to use both of them in the derivation to figure out this y of t. Okay. And we'll discuss it in the next part of the video.